So I read on the internet this one time that something like half of the English language comes directly from French vocabulary, which maybe isn't too surprising if you've studied languages, but I found that pretty interesting. And so did the French writer Alexandre Dumas. He was teaching himself English, and while reading an English book, he noticed the similarities to French, and he exclaimed to himself, well, English is merely French, just badly pronounced. This may be an apocryphal story, I don't know, but it's nice for this talk. This is a talk about finding functional patterns in unexpected places. As Dumas found with his French vocabulary, we can find that recognizing functional programming patterns in unfamiliar systems can actually help us better understand both those systems and our own concepts from functional programming. So in this talk, we're specifically going to take our knowledge of functional programming and see how we can use that to reason about software-defined radio. And we'll do that by looking through the lens of category theory. So we'll break this up into 4 sections, and please stop me with any questions along the way. There's going to be a lot of material, especially if you don't have a background in signal processing or category theory or functional programming. I encourage you to ask any questions, and I can clarify things as we go. But otherwise, we'll start with a simple technique that I like to use for visualizing categories, which will be very informal. I'm not a mathematician by any stretch. And then we will go into 3 basic concepts from category theory, and that's function composition, functors, and natural transformations. For each one of these, I'll briefly introduce the theory. Then we'll take a familiar example from functional programming and see how we can use that to learn about software-defined radio. So let's start with visualizing categories. At its core, a category is really just a collection of objects and arrows. And again, this is very informal. So given a category C, it has some arbitrary objects, x, y, z, and some arbitrary arrows, x to y, y to z. You might recognize this in terms of programming where your x, y, z might be some types, and your arrows, x to y, y to z, might be some function types. There's some other things in a category that we will get to, like the composition operator, and there's a whole lot of stuff that we're not going to cover. We're just going to skip over, like laws and things like that. So in programming, we can use category theory to think about the category of types. So in the category of types, our objects are very simple, flat types like int or string or some class that you might write. And arrows are just functions between them. So there could be an arrow from int to string or string to int in this example. And these are just functions that take an int and produce a string or take a string and produce an int. And thinking about programming in terms of this category of types, can be really useful for helping reason about the sort of domain of possible program types that we can write. We can also think of not just flat types as a category, but type constructors as a category. So for example, we might think about option or the option type constructor as itself a category. And in this category, our objects are options of things. So we might have an option of A or option of B. That could be an option of int or string or whatever. These are objects in our option category. And similarly, arrows in the option category go from one option to another. So I'm a function, you give me an option of A, and I'll spit out an option of B. And this isn't limited to any one type constructor, so we can start adding as many of these as we like. So think about the category of the list type constructor. So just like with option, objects in this category are lists of things. So we could have a list of A, a list of B for some types A and B. And arrows in this category are just functions that operate on lists of things. Okay, so that is visualizing categories as they apply to programming. Now let's see how they apply to radio. And before we go there, I want to kind of give a quick overview of what we're actually using here for our radios. So we will be transmitting and receiving a simple signal. And to do that, we'll be using a HackRF1, which is just an off-the-shelf software-defined radio that you can buy. And there's a wealth of software out there that you can use to drive the thing. We will be using GNU Radio, specifically GNU Radio Companion, which is a GUI graphical front end on top of GNU Radio, which we'll get into depth in a minute. We're also going to be receiving the signal on actually a digital TV tuner. These are really, really inexpensive off-the-shelf devices that were originally intended for receiving TV signals over the air until it was discovered that they're actually a very cheap software-defined radio receiver. And so they're very popular to use in decoding all kinds of signals across the radio spectrum. So we'll be driving the receiver with this program called GQRX, which looks something like this. This is nice because it gives us a waterfall diagram so we can see signals over time across a band. And I'm also using this cheap handheld transceiver to receive the signal. That way we can hear it when we transmit it and on something that's not actually connected to my computer, so you know that it's really going over the air. Okay, so in GNU Radio, which I've got here, this is how we build a software-defined radio in GNU Radio. So in this example, we have a very simple radio. They're based on these 5 blocks. And I should point out, in GNU Radio, everything is done graphically using blocks and connections between blocks. And so the way to think about this is each of these blocks is some operation that can operate on a signal. A signal is some series of sampled values over time. So in this radio, and everything flows from left to right in this flow graph. So we have 5 blocks in our radio. We have a source, and that's producing a Morse code signal that we're going to eventually transmit. That block then sends the signal to the next block, which is an amplifier. This amplifier actually reduces the amplitude by half because we don't actually need to transmit very much power for this demo. That amplified signal then goes to the third block, which is our narrowband FM modulator. And that just takes our signal and modulates it so that it can be transmitted and received using narrowband FM, which is a common way to modulate and demodulate a signal. I should point out, narrowband FM is really inefficient way to send Morse code, and no one actually does it that way. But it makes for a nice demo because we can receive it on hardware like this. So once we've modulated the signal, we want to filter out any high-frequency components that may have been introduced by the math or anywhere else and that we do not want to transmit. So we get rid of those. And then finally, we pass our signal to a sync, which in this case is just a driver for that hack RF. So I'm going to spin this up, and hopefully we can hear it. Before I do, let me switch frequencies here. So we're going to be on the UHF band. And we're going to watch on this waterfall diagram and listen on the little handheld radio. So. Note that it's not attached. Okay, so we had to end that transmission with my call sign so that it's nice and legal. All right, so let's go back to our radio. We can stop this from transmitting. Okay, so tying this back to how we came into this, we were talking about visualizing categories. So this flow graph is itself implemented in Python, and under the covers, all of the signal processing in GNU Radio is done in C or maybe C++. There's not really any advanced type theory going on in either of those two languages, but that's okay. As just a user of the companion, this graphical flow graph, we can still reason about it in terms of categories. So our flow graph has 2 main things. It has these blocks, which, as I said, are operations on signals, and it has the connections between them, which kind of represent the signals feeding from one block to the next. And so it turns out that signals are like an object in a category, and blocks are like an arrow. So our signals are discrete values, and if you're familiar with functional reactive programming, you may recognize this. Even though a signal is values over time, it's still a singular thing. It's an object in our flow graph category. And blocks are functions that take a signal and produce a signal, so they are arrows on the category. So we're going to use this through the rest of the talk and build on it. But the the key takeaway here is that if we're looking at a system, in this case a radio, as long as we can identify objects and arrows and be a little bit informal about the laws of category theory, we can use categories to really visualize anything. Okay, before we move on to composition, are there any questions on what we just saw? Sweet. So in category theory, a category has more than just objects and arrows, and one of the things that it has is a composition operator. And all this does is assemble pairs of arrows. So here's our category from before. We have our objects x, y, z. We have arrows x to y and y to z. So if we wanted, for example, an arrow from x to z, we could assemble these two using composition to get it. So we take y to z, compose it with x to y, and that gives us x to z. And note how the arguments to the composition operator are sort of reversed. We have the first function that will ultimately be applied as kind of the inner value in this composition, or the second argument. But mostly that's just convention. In functional programming, we have composition, and it takes a few different forms depending on what language you're coming from. For example, Haskell has the dot operator, so this says n compose m. Scala has the and then and compose methods, which basically do the same thing, although their orders are reversed from each other. But all of these are really just no different from a simple lambda expression that, given some input, applies it to m, and then applies that to n, and spits out the result. So let's find composition in our radio. I'm going to drill down into this block, which is our source. And as you can see, it's actually built from many lower level blocks. And it turns out this is composition. So in our radio, we have this nice high level abstract thing. It's just 5 blocks: a source, an amplifier, a modulator, a filter, and a sink. But to build that source, it takes a lot more. We have to have the actual Morse code that we want to send, and a carrier on which we want to transmit that. And we also have a throttle, which is a sort of side effect of how GNU Radio works, and a sink. And so to keep all of this complexity off of our primary flow graph, we make this sort of sub block by composing all of these components together. So let's look at how we can think about composing blocks. So let's abstract this to just m and n. If we have 2 blocks, and maybe these are lower level blocks, like in our source here, we want to put them together into a logical higher level block called m and then n. So in practice, this is just wiring them directly together. You wire the output of m to the input of n. But this is actually composition. So m and then n is the same as n compose m. So composition is great for hiding complexity. We can take really as many functions as we want and start putting them together like we've done here. So we've actually composed more than just 2 arrows here. We've composed arrows with more arrows with more arrows until we're kind of at the right level of abstraction that we want. Okay, let's talk about functors. In category theory, a functor is essentially a mapping between categories. A functor can map objects from one category into another, and it can map arrows from one category into another. So here we have categories C and D, and we have the category of functors, which just has one functor F. So we would say that F, in this case, is a functor from C to D. And it can map objects. So here we're taking a C object called A, and we're turning it into a D object called f of A, using the F functor. And we can do the same thing for arrows. So given a C arrow, A to B, we can turn that into a D arrow, F of A to F of B. And as we'll see, this is really useful for cases where maybe we already have an F of A, and we have an arrow A to B, and we want to be able to apply that arrow to that object. To do so, we need to use something like a functor to pull it into the D category so that its input matches the type of object that we're dealing with. In programming, we have, particularly in functional programming, we have something very similar, but there's one interesting difference, and that's that to map objects in our categories, we're not using a functor. We just use a type constructor. And as far as I understand, this is a practical limitation of basically the way our type system works. But essentially, we have the same thing through a combination of type constructor and functor. So let's quickly dive into this. So we have our category of plain types, like int and string. We have our category of optional types, like option of int, option of string. And to map objects from one to the other, we use the option type constructor. But to map arrows from one to the other, we use a functor. And so in this case, our functor is from the category of types to the category of options of types. The way this is implemented typically in languages like Haskell or in Scala libraries like Scala Z or CATS is just as a type class. So the way we can read this in terms of that diagram is given an arrow A to B, and I'll go back, that's this arrow, we can pull that into the option category to make an f of A to f of B. So you give me an A to B, and I will give you a function that then takes an f of A and returns an f of B. And that's exactly what we see here. So this is our function A to B. This is our functor mapping it and turning it into a function that takes an f of A, where f is option here, and returns an f of B. And here's a concrete example of that. So let's say we want to turn, actually this is exactly what we have on the previous slide. So a functor for option has to be able to take any arbitrary A to B arrow and turn it into an option of A to option of B arrow. And it's pretty simple to implement this. We just pattern match on what this option is, and if it's none, there's really nothing to do. If it's sum of A, meaning this option has some A value in it, then to produce an option of B, we just pass that A value to this function from the types category. In object-oriented languages like Scala, we'll sometimes see functors implemented slightly differently, in this case as a method on some option-like type. So what this says is there exists a type option, and it has a parameter A. To map functions into that category, we have a very similar function that takes our A to B and returns a function option A to option B, which is sort of encapsulated by this whole trait. So once again, given our A to B, we can then take an option of A and produce an option of B. This is the same thing we saw on the previous slide, just a slightly different way to do it. So let's find a functor in our radio. Specifically, I want to look at the amplifier block here. Up until now, I've been talking about signals as sampled values over time. These are digital signals. But amplification is itself a function that, while it's operating on these signals over time, it actually doesn't care about time. The way it amplifies has nothing to do with when the signal is happening or how the signal is changing over time. It just takes numbers as an input, multiplies them by a constant, and spits them out. So it's actually useful to think about, to sort of divorce the amplifier from the concept of time and think about it differently. So for example, imagine we have a signal in time, which we call a time domain signal, f of t, where t represents time. That signal might be something simple like a sine wave. So our signal varies in time as a sine wave. Our amplifier, on the other hand, as I said, it doesn't care about time. So we would represent that perhaps as f of x, where x is supposed to indicate that time doesn't matter. And so these are two types of signals that kind of relate to the slide we saw on types and options of types. So we have sort of undesignated signals and time domain signals. And it turns out that it's really useful to think of these as two separate categories. So there's a lot here, so let me go through it. So f of t, as I said before, is a signal. It's a time domain signal. It's just sine of t. And so that is an object in the time domain signals category that we just made up. F of x, on the other hand, that's our amplifier. That's just a function that takes a number and spits out a number. It doesn't care about time. So we put that in the signals category as an arrow. So our amplifier, we know, is taking this function and applying it to a time domain signal. So there's actually, we can reason about a implied functor somewhere that knows how to convert signals into time domain signals, as well as signal arrows into time domain signal arrows. So for our amplifier to work with this model, we imagine this functor taking our amplify function, our amplify arrow, and pulling it into the time domain signals category so that we can apply our time domain signal f of t to it. So the key takeaway is that functors are essentially a way for us to use objects and arrows from some different category. If we're given a time domain signal from this category and we're given an arrow from a different category, as long as we have a functor that maps between those two categories, we can apply them in a different category. All right, now let's move on to natural transformations. And this one will be a lot, so please stop me if you have any questions. Okay, so let's imagine three categories, C, D, and E. And C has one object, X. Now let's add a functor, F. So F is a functor mapping C to D, just like we saw before. So given some C object X, if we need to make a D object out of it, we can use the F functor to do so. And we're going to ignore arrows for a minute. Similarly, if we have a C object X and we want a E object out of it, we can use a G functor, which is a functor from C to E. So a natural transformation is, in category theory, is an arrow between functors. And this is how we might represent it. So given a natural transformation P, it's an arrow between these two functors F and G. So remember, these are our functors. And so given everything that we've got here, if we have an f of x that was produced by this f functor, and we want to get a g of x, we can use this natural transformation to produce it for us. So it will take us from this f of x to this g of x. Then we can add another one in the reverse so that we can go back in the other direction. In functional programming, we see natural transformations usually as a squiggly arrow like this. But you can see that underlying P arrow from before is here. So you give me an f of a, and that's this guy over here. And I will give you a g of a, and that's this one over here. So here's an example natural transformation from option to list. So this says, if you give me an option of a, I will give you a list of a. And again, that's pretty simple. A none turns into the empty list, and a sum turns into a unary list. Something interesting here is that this natural transformation, and if I go back, the generalization of it actually has nothing to do with functors. At least we haven't declared it in terms of functors, even though we know from category theory that a natural transformation is an arrow between functors. So that's kind of a practical limitation, but it's still interesting to think about. If we have a natural transformation, there must be some functors somewhere, even if they're just notional. And for those functors to exist, there must actually be a third implied category. And so that might look like this, the category of types, which we've seen before. So from our category of types, we can get to option or to list using functors, right? So option, the type constructor, is essentially a functor that turns A into option of A. List, the type constructor, is a functor that turns A into list of A. And then, so option to list turns out to be a natural transformation between these two functors, O and L. All right, so we're running out of time, so I might have to rush through this part. But one thing I wanted to talk about to get us to natural transformations in our radio is the frequency domain. So I'm going to do this really quick. Okay, so imagine a signal that is produced by summing 4 different sine waves. And here are our 4 sine waves at the top. And here is the result of summing them in time. Turns out there's another way to represent signals, and that's with frequency as the dependent variable. So over here we have a time domain signal that's the sum of 4 sine waves. Over here we have a frequency domain signal, which is the same. It's a sum of 4 sine waves. And so what we're looking at is there's 3 points, which they're sort of represented as spikes here. 4 points represented as spikes, each representing a sine wave at a particular frequency. So these 2 graphs at the bottom, this time domain signal and this frequency domain signal, are showing the exact same information. They're just different ways of representing it. Okay, so now that we know a little bit about the time domain and the frequency domain, I want to show you how we can use that to build a digital filter. And this is actually what we're using in our radio here. And I'm going to have to rush really quickly through this. So let's look at our filter. Okay, so here are our 4 spikes from before. These are our 4 sine waves in frequency. And in green, hopefully you can see there's another function on here, which is sort of a square wave. And on the right, we have the product of these 2. So it's 0 everywhere because the green signal is only defined right here, and it's 0 everywhere else. And then likewise, the blue signal is defined on these 4 points and 0 everywhere else. So when we multiply these things together, we get just a bunch of zeros. But if we make that green signal a little bit wider, so that it overlaps one of these spikes, then the output is non-zero at that one point where they're both non-zero. And if we keep making this thing wider and wider, you can see that our output includes more and more of the input because we're multiplying these 2 signals together and they're zeroing each other out less and less. And this is the concept of a digital filter. If we have this source signal with these 4 sine waves, but we only want 3 of them in the output, for example, all we have to do is come up with a signal that we can multiply together and zero out the stuff that we don't want. I apologize for rushing. This is a lot. So let's look at our actual transmit filter that we have here. So the way that this filter works is it uses exactly this principle. So it takes a signal, a time domain signal, converts it into the frequency domain so that we can do this frequency domain multiplication, converts it back into the time domain, and then spits it back out. And it turns out that this is a natural transformation. So using our time and frequency domains as categories as before, imagine we have a time domain signal, that's our samples over time coming into the filter. We need a frequency domain signal so that we can multiply it and filter components that we don't want. So we have to convert our time domain signal into a frequency domain signal. And in DSP, this is done using the Fourier transform. But really, this is actually a natural transformation because we're converting this constructed type into that constructed type. And then we have to go back in the other direction. And in practice, this is done with an inverse Fourier transform. And it turns out that that is also a natural transformation because it's taking us from this constructed type to that one. And just like before, we're sort of ignoring the middle category, and we can infer that there actually must be functors for both of these to be natural transformations. So the takeaway is that natural transformations convert values between types constructed by some functor. So we've got a time domain signal, we need a frequency domain signal. These are 2 categories. We can use a natural transformation to do so. So hopefully this has shown that recognizing functional patterns in places that we didn't expect to find them can help us reason about those systems as though we were doing functional programming, even though, as I said, this is all Python and C. And also, I find that this helps me understand the functional programming patterns better because it's just a new perspective on those same ideas that I may have already been developing. Okay, so we're a little bit over time. This talk was based on this paper, Categories for the Working Hardware Designer, which I highly recommend if you're interested in this idea. And where we used DSP, the author of this paper used, she wrote a hardware definition language, I think for VLSI design or something. But it's a really neat paper. And then if you're interested in category theory, everything I did in this talk was based on this book by Pierce. And if you're interested in signal processing, find me after and we can play with these radios, or you can check out the book by Owen. So I think maybe we'll take questions offline. Yeah, okay, cool. Thank you.